Look up on a clear night, far from city lights, and you'll see a pale band of light stretching across the darkness like spilled milk across velvet. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. The Romans knew it as Via Lactea, the road of milk. Every civilization that has gazed upward has wondered at this luminous river flowing through the heavens, never knowing they were looking at their home from the inside. To truly grasp the scale of what we're discussing, we need to put the Milky Way's size into context that our human minds can begin to process. The visible disk of the Milky Way, that 100,000 light-year span, represents a distance so vast that if you could somehow travel at the speed of light, the fastest speed possible in our universe according to Einstein's relativity, it would take you 100,000 years to cross from one edge to the other. Light travels at 186,282 miles per second, or roughly 671 million miles per hour. At this incomprehensible speed, you could circle Earth's equator more than 7 times in 1 second. You could reach the Moon in about 1.3 seconds. You could arrive at Mars in a few minutes when the planets are closest. Yet even at this speed, crossing the Milky Way would require an entire geological epoch. To put this another way, if the Sun emits a photon of light today heading toward the far side of the galaxy, that photon will still be travelling through interstellar space when human civilization as we know it has long since risen and fallen, when our distant descendants, if they exist, have evolved into forms we might not recognise, when continents have drifted into new configurations and new mountain ranges have risen while others eroded away. The scale defies intuition. It mocks our everyday experience of distance and time. Consider another comparison. The distance from Earth to the Sun, called an astronomical unit, measures about 93 million miles or 150 million kilometres. This is already a distance beyond everyday human experience. Light from the Sun takes about 8.3 minutes to reach Earth, meaning we see the Sun not as it is now, but as it was 8.3 minutes ago. If the Sun suddenly vanished, we wouldn't know about it for more than 8 minutes. This astronomical unit, this Earth-Sun distance that already seems so vast, fits into the Milky Way's diameter more than 600 million times. Stack 600 million Earth-Sun distances end to end, and you would span the visible galaxy. The entire solar system out to Neptune's orbit, encompassing all the planets and most of the objects we commonly associate with our cosmic neighbourhood, has a diameter of about 60 astronomical units, or roughly 5.6 billion miles. The Milky Way's visible disk is approximately 10 million times wider than the solar system. If you shrunk the solar system down to the size of a quarter, the visible Milky Way would stretch from the Atlantic to the Pacific coasts of North America. And that's just the visible disk, not counting the dark matter halo that extends 20 times farther. For most of human history, we had no idea what we were seeing. We lived inside a cosmic mystery surrounded by something so vast that comprehending it seemed impossible. The stars we could see with our naked eyes numbered only in the thousands, scattered points of light that gave no hint of the enormous structure containing them. We were like microbes living on a grain of sand at the bottom of the ocean, trying to understand the ocean itself by looking around at the water immediately surrounding us. Even the nearest star to our Sun, Proxima Centauri, lies 424 light-years away, a distance of about 25 trillion miles. If you could somehow drive a car through space at highway speeds, say 70 miles per hour, it would take you over 40 million years to reach Proxima Centauri. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of over 430,000 miles per hour during its closest approaches to the Sun. Even at this blistering pace, it would take over 6,600 years to reach our nearest stellar neighbour. And Proxima Centauri is just the first star beyond our Sun. The Milky Way contains hundreds of billions of such stars, scattered across distances that make the journey to Proxima Centauri look like a walk to the corner store. The number of stars alone defies comprehension. If we take a middle estimate of 200 billion stars and imagine trying to count them, allocating just 1 second to each star, the task would require over 6,300 years of continuous counting, 24 hours a day, without breaks for sleep or food or anything else. This is longer than recorded human history. You would have to start counting before the pyramids were built and continue to the present day to count every star in the galaxy. And this doesn't even account for the fact that stars are constantly being born and dying, that the galaxy is dynamic, that the sensors would be obsolete before you finished it. But humans are persistent creatures. We built telescopes, we developed mathematics, we created instruments that could see what our eyes could not. And slowly, painfully, over centuries of observation and calculation, we began to grasp something profound. We were not looking at a small collection of nearby stars. We were embedded within a colossal island of stars, gas and dust, a spiral-shaped city of light containing hundreds of billions of suns, stretching across distances so large that light itself, racing at 186,000 miles every second, takes 100,000 years to cross from one side to the other. The Milky Way galaxy, our cosmic address. Our home on the largest scale imaginable, and for all our progress, for all our technological achievements, we are only now, in 2024, beginning to understand just how big it really is. The measurements that came out this year shattered assumptions that had stood for decades. Scientists thought they knew the size of the Milky Way. They were wrong. The new data reveals a galaxy that is larger, more massive, and more complex than our previous models predicted. The numbers are staggering, the implications are profound, and the methods used to arrive at these conclusions represent some of the most sophisticated astronomical detective work ever conducted. This is the story of how we measured the immeasurable, how we weighed the unweighable, how we finally figured out the true dimensions of the cosmic wheel on which we ride. The journey begins over a century ago with a young astronomer who dared to challenge everything his colleagues believed about the universe. Before Harlow Shapley could revolutionize our understanding of the Milky Way's size, centuries of astronomers had to lay the groundwork, building the tools and techniques that would make his measurements possible. The story of measuring the galaxy actually begins much earlier, in an era when the very concept of measuring cosmic distances seemed impossible. In 1610, when Galileo Galilei first pointed his crude telescope at the Milky Way, he made a discovery that would shake the foundations of astronomy. That mysterious band of light resolved into countless individual stars too faint and numerous to see with the naked eye. What appeared as a milky glow to unaided human vision revealed itself as a vast congregation of discrete suns. Galileo's observation shattered the Aristotelian view that the Milky Way was some sort of atmospheric phenomenon or celestial fire. It was made of stars, but the implications of this discovery would take centuries to fully understand. The German philosopher Immanuel Kant in 1755 proposed a radical idea that our sun was part of a flattened system of stars, what he called an island universe. He suggested that the pale band of the Milky Way was simply our edge on view through this disk of stars, and that the faint nebulous patches scattered across the sky might be other island universes, other Milky Ways at enormous distances. It was a prescient speculation, remarkably close to our modern understanding, but Kant had no way to prove it. The tools did not exist to measure the distances that would confirm or refute his theory. Enter William Herschel, perhaps the most industrious observational astronomer of the 18th century. Born in Hanover, Germany in 1738, Herschel came to England as a musician before becoming consumed by astronomy. He built his own telescopes, grinding mirrors that were the largest and most powerful of their time. His 40-foot telescope, completed in 1789, had a mirror 48 inches in diameter and remained the largest in the world for half a century. With these instruments, Herschel embarked on a systematic program to count the stars and map the structure of the heavens. Herschel's method was simple in concept but extraordinarily laborious in execution. He would point his telescope in different directions across the sky, count how many stars he could see in each field of view, and use these numbers to infer the shape and extent of the stellar system. His crucial assumption was that all stars had roughly the same intrinsic luminosity. Under this assumption, a fainter star was simply more distant. By counting stars in different directions and noting how the counts varied, he believed he could determine in which directions the stellar system extended farthest. Between 1784 and 1802, Herschel and his sister Caroline, herself an accomplished astronomer, conducted these star counts in 683 different regions of the sky. The project consumed thousands of hours of observing time, night after night of counting and recording. What emerged from this monumental effort was a model of the Milky Way as a flattened disk, with the Sun positioned near its centre. Herschel estimated the disk extended roughly 1,000 times farther along its plane than perpendicular to it, giving it a decidedly pancake-like shape. He placed the visible extent at perhaps 1,500 light-years in radius, though his actual measurements used different units, and his concept of a light-year was not the same as ours. The model was correct in recognizing the flattened shape, but spectacularly wrong about nearly everything else. The Sun was not at the center. The galaxy was vastly larger than Herschel estimated, and most critically, his assumption about uniform stellar luminosity was incorrect. Stars vary enormously in their intrinsic brightness. A blue supergiant can be hundreds of thousands of times more luminous than a red dwarf. Herschel's method could not account for this variation, leading to systematic errors that undermined his distance estimates. Moreover, Herschel could not see through the interstellar dust that fills the galactic plane. In directions where dust clouds blocked his view, he saw fewer stars and concluded incorrectly that the stellar system did not extend as far in those directions. It was like trying to map a city while standing in a neighborhood where fog blocks your view in certain directions. You would naturally conclude the city ended where the fog began, never realizing that buildings continued beyond the visible edge, hidden by the obscuring mist. Despite these limitations, Herschel's work represented genuine progress. He established that the Milky Way had structure, that it was not an infinite uniform distribution of stars but rather a bounded system with a definite shape. He catalogued thousands of nebulae, those fuzzy patches that would later prove to be a mix of gaseous nebulae within our galaxy and external galaxies far beyond. His son, John Herschel, continued this work, extending the observations to the southern hemisphere and cataloguing celestial objects that his father, observing only from England, could never see. By the mid-19th century, astronomers had begun to grapple with the question of distance more seriously. In 1838, Friedrich Bessel made the first successful measurement of stellar parallax, determining that the star 61 Cygni was about 10.3 light-years away. This was a breakthrough. For the first time, humans had measured the distance to a star using geometry rather than speculation. The method used the Earth's orbit as a baseline, measuring how a nearby star appeared to shift position against the backdrop of more distant stars as Earth moved from one side of its orbit to the other. But parallax only worked for the nearest stars. Even with the best instruments of the 19th century, parallax measurements were limited to stars within about 30 light-years. This was a tiny bubble compared to the extent of the Milky Way. Astronomers needed a way to bridge from these nearby parallax measurements to much greater distances, and that required understanding stellar properties, developing what would become known as standard candles, objects whose intrinsic luminosity could be determined independently of their distance. Various attempts were made. Spectroscopy, the analysis of starlight broken into its component wavelengths, revealed that stars could be classified by temperature and composition. Certain spectral features correlated with luminosity, offering a way to estimate a star's true brightness. But the correlations were imperfect, and uncertainties remained large. What astronomers needed was a class of objects with a reliable, simple relationship between an easily observable property and intrinsic luminosity. They needed something like Henrietta Leavitt's Cepheid variables, but that discovery still lay in the future. By 1900, the best estimates placed the Milky Way's extent at perhaps 10,000 to 30,000 light-years, with the Sun at or near the centre. This was still wrong, but getting closer to reality. The stage was set for the revolutionary insights that would come in the 1910s and 1920s, insights that would require both new observations and new ways of thinking about the data astronomers had already collected. The year was 1917. The world was engulfed in the horrors of the First World War. Empires were collapsing. Millions were dying in trenches that stretched across Europe. But high in the mountains of Southern California, isolated from the chaos below, a 31-year-old astronomer named Harlow Shapley was engaged in a different kind of revolution. Mount Wilson Observatory sat above the smog and light pollution of Los Angeles, its 60-inch reflecting telescope pointed at the heavens. This was one of the most powerful astronomical instruments in the world, capable of gathering enough light to reveal stars too faint for any human eye to see, even with smaller telescopes. The observatory itself was a marvel of early 20th century engineering, perched at an elevation of 1,642 meters, on a peak that offered exceptionally clear viewing conditions for much of the year. On the clearest nights, astronomers could see details in celestial objects that had been completely invisible to previous generations. Shapley had come to Mount Wilson after completing his doctorate at Princeton University under Henry Norris Russell, one of the leading astrophysicists of the era. His dissertation had focused on eclipsing binary stars, pairs of stars orbiting each other in such a way that one periodically passes in front of the other as seen from Earth, causing regular dips in the combined brightness. By analysing the timing and depth of these eclipses, Shapley had developed methods for determining the sizes and masses of the stars involved, measurements that were impossible to obtain any other way at the time. His work had established him as a rising star in astronomy, someone who combined mathematical skill with observational precision. But Shapley's ambitions extended far beyond measuring individual stars. He wanted to understand the structure of the entire galaxy. Night after night, he exposed photographic plates to the faint light of globular clusters, those dense spherical swarms of ancient stars that orbit our galaxy like bees around a hive. Each exposure took hours, the telescope tracking the cluster's motion across the sky as Earth rotated, accumulating photons one by one until enough light had been captured to reveal stars invisible to direct observation. He was searching for variable stars within these clusters, stars that pulse in brightness with mathematical regularity. More specifically, he was hunting RR Lyrae variables, stars that brightened and dimmed on predictable schedules lasting anywhere from half a day to just over a day, their periods of variation directly related to their intrinsic luminosity. These stars are inherently luminous giants, hundreds of times brighter than the Sun, making them visible at enormous distances despite their individual faintness in our telescopes. This relationship between period and luminosity had been discovered a few years earlier by Henrietta Swan Leavitt, a woman working as a computer at Harvard College Observatory for a mere 30 cents an hour. Leavitt's discovery was revolutionary, though she likely never fully realised it. If you could measure how fast a variable star pulsated, you could determine how bright it actually was. Compare that intrinsic brightness to how bright it appeared from Earth, and simple mathematics would tell you how far away it must be. For the first time in human history, astronomers had a reliable cosmic ruler, a standard candle that could illuminate the distances to objects millions of light years away. Leavitt's story deserves a moment of recognition because her contribution to astronomy, while eventually acknowledged, took decades to receive proper credit. Born in 1868 in Lancaster, Massachusetts, she graduated from what is now Radcliffe College in 1892 and joined Harvard College Observatory as a volunteer in 1893. Her role, like that of many women in astronomy at the time, was considered clerical rather than scientific. She was part of a group of women hired by Observatory Director Edward Charles Pickering to analyse photographic plates, measuring and cataloguing the positions and brightnesses of stars. The work was repetitive, detail-oriented and poorly paid, but it allowed these women access to astronomical data at a time when they were barred from using telescopes themselves or holding official scientific positions. Leavitt specialised in variable stars, stars whose brightness changed over time. Between 1908 and 1912, she studied over 1,700 variable stars in the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere. What made these galaxies ideal for her study was that all their stars were approximately the same distance from Earth. This meant that differences in apparent brightness corresponded directly to differences in actual luminosity. A star that looked brighter really was more luminous. A star that looked dimmer really was less luminous. There was no distance ambiguity to confuse the interpretation. Within this sample, Leavitt identified a clear pattern among the Cepheid variables. The longer a Cepheid's period, meaning the more time it took to complete one cycle from bright to dim and back to bright again, the more luminous it appeared. This was not a subtle effect. The relationship was clear and systematic. Plot the period against the luminosity on a logarithmic scale, and the points fell along a straight line with only modest scatter. This was a fundamental law, a period luminosity relationship that held for all Cepheid variables regardless of their individual properties. The implications were staggering, though they took time to fully materialise. If you observed a Cepheid variable anywhere in the universe, measured its period by watching how it pulsed, you could use Leavitt's relationship to determine its true luminosity. Knowing the true luminosity and measuring the apparent brightness gave you the distance through the inverse square law of light propagation. Light from a source spreads out in 3 dimensions as it travels, so the intensity falls off as the square of the distance. Double the distance and the brightness drops to 1/4, triple the distance and the brightness drops to 1/9. The mathematics was straightforward once you had the tools to apply it. Shapley recognised immediately that this method could revolutionise distance measurements within the Milky Way and potentially beyond. But there was a complication. Leavitt's period luminosity relationship gave relative distances, not absolute ones. You could determine that one Cepheid was twice as far as another, or that a particular star was 3 times more distant than a reference object, but you needed to know the distance to at least one Cepheid independently to calibrate the entire system. Without that calibration, the scale remained uncertain. Calibration came from parallax measurements of nearby Cepheids, stars close enough that their position shifted measurably as Earth orbited the Sun. Parallax is the apparent displacement of an object when viewed from different positions, the same effect that makes your finger seem to jump when you alternately close your left and right eyes. For stars, the parallax is tiny, measured in fractions of an arcsecond, but observable with sufficiently precise instruments. By 1913, the Danish astronomer Einar Hertzsprung had used parallax to estimate the distance to a few nearby Cepheids, providing the calibration needed to convert Leavitt's period luminosity relationship into an absolute distance scale. Armed with this tool, Shapley set out to measure the distances to globular clusters throughout the galaxy. Shapley used this tool with stunning effect. He measured the distances to 93 globular clusters, painstakingly determining where each one sat in 3-dimensional space. When he plotted their positions, a pattern emerged that shocked him. The globular clusters were not scattered evenly around the sky. They were not centered on Earth's position. Instead, they formed a rough sphere around a point far from the solar system, a point that lay in the direction of the constellation Sagittarius. The implication was inescapable. Globular clusters, Shapley reasoned, must outline the true extent of the galaxy. They marked its boundaries, its overall structure. And if they formed a sphere around a distant point, that point must be the center of the galaxy itself. Which meant Earth and the Sun were not at the center of anything. We were not in a privileged position. We were out in the suburbs, roughly 30,000 light-years from the galactic core, residents of an unremarkable neighborhood in the cosmic city. More shocking still was what this implied about the galaxy's size. If the Sun was 30,000 light-years from the center, and globular clusters extended out in all directions, the Milky Way must be enormous, perhaps 100,000 light-years in diameter. This was 10 times larger than most astronomers believed. Before Shapley, the consensus held that the Milky Way was perhaps 10,000 to 30,000 light-years across, with the Sun near its center. Shapley's numbers demolished this comfortable geocentrism. The resistance was immediate and fierce. Many astronomers refused to believe such radical claims. The controversy came to a head in 1920 with the famous Great Debate between Shapley and astronomer Heber Curtis. They argued before the National Academy of Sciences about 2 fundamental questions. How big is the Milky Way? And what are those fuzzy, spiral nebulae astronomers could see scattered across the sky? Shapley argued for a huge Milky Way containing all the matter in the universe. Curtis argued that spiral nebulae were separate island universes, other galaxies like our own, scattered through a cosmos far larger than anyone had imagined. Ironically, both men were partially right and partially wrong. Shapley was correct about the Milky Way's enormous size, but wrong about spiral nebulae being part of our galaxy. Curtis was right about spiral nebulae being separate galaxies, but wrong about the Milky Way being small. The debate was settled a few years later by Edwin Hubble, who used the new 100-inch telescope at Mount Wilson to identify Cepheid variables in the Andromeda Nebula. His measurements proved beyond doubt that Andromeda was far too distant to be part of the Milky Way. It was indeed a separate galaxy, containing hundreds of billions of its own stars. When Shapley received Hubble's letter showing the data, he reportedly told a colleague, "Here is the letter that destroyed my universe." But Shapley's fundamental insight about the Milky Way's size proved remarkably durable. His estimate of 100,000 light-years in diameter has held up with remarkable accuracy over more than a century of subsequent observation. Even as our tools have grown more sophisticated, as we have launched spacecraft beyond Earth's atmosphere and built telescopes that can detect individual stars billions of light-years away, Shapley's basic measurement remains valid. the visible disk of stars and gas in the Milky Way does indeed span roughly 100,000 light-years from edge to edge, that single number, 100,000 light-years, captures something profound about human capability. An astronomer working with photographic plates and manual calculations, using a telescope built with 1910s technology, managed to accurately measure a structure so vast that light from one side takes longer to reach the other side than modern humans have existed as a species. It stands as one of the great intellectual achievements in the history of science. But as we will see, that number tells only part of the story. The Milky Way is not just a flat disk of stars. It has layers, extensions, hidden components that dwarf even the visible spiral that Shapley measured. The journey to understanding the galaxy's true size was just beginning. Understanding how astronomers measure the Milky Way today requires appreciating the diverse toolkit they have developed, each technique suited to revealing different aspects of the galaxy's structure. These are not simple measurements. They represent the culmination of decades of theoretical development and technological innovation, combining observations across the electromagnetic spectrum with sophisticated computer modeling and statistical analysis. The most fundamental measurements involve mapping the distribution of stars throughout the galaxy. This sounds straightforward, but the practical challenges are immense. We cannot see most of the galaxy's stars individually. Even Gaia, with its unprecedented capability to measure 1 billion stars, captures less than 1% of the galaxy's total stellar population. The rest must be inferred through indirect methods, statistical analyses that use the stars we can see to estimate the properties of those we cannot. One powerful technique involves measuring surface brightness, the amount of light coming from a given patch of sky. By carefully measuring how this brightness varies in different directions and at different distances from the galactic center, astronomers can reconstruct the distribution of stars. But this method requires meticulous calibration and correction for numerous effects. Interstellar dust absorbs and scatters light, making distant regions appear dimmer than they actually are. The correction for this absorption depends on knowing how much dust lies along each line of sight, information that must be determined from independent observations. Spectroscopy provides another crucial tool. When starlight passes through a spectrograph, it splits into its component wavelengths, creating a spectrum that encodes vast amounts of information. Absorption lines in the spectrum reveal the star's chemical composition, its temperature, and its surface gravity. From these properties, astronomers can infer the star's mass, age, and intrinsic luminosity. Knowing the true luminosity and measuring the apparent brightness gives the distance through the inverse square law. But spectroscopy becomes challenging for distant, faint stars. Collecting enough light to produce a useful spectrum requires large telescopes and long exposure times. For the faintest objects, even hours of observation with the world's largest telescopes barely capture enough photons to analyze. This limitation means that spectroscopic surveys cannot reach the galaxy's most distant regions or probe its faintest stellar populations comprehensively. Radio astronomy provides a way to see through the dust that obscures optical observations. Neutral hydrogen, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. This emission arises from a quantum mechanical transition in the hydrogen atom, a flip in the spin orientation of the electron relative to the proton. The transition is rare for any individual atom, occurring perhaps once every 10 million years, but with so many hydrogen atoms in the galaxy, the collective emission produces a strong signal that radio telescopes can detect. By mapping the 21 centimeter emission across the sky and measuring its Doppler shift at each location, astronomers can trace the distribution and motion of hydrogen gas throughout the galactic disk. The Doppler shift reveals whether the gas is moving toward or away from us, and the magnitude of the shift indicates the velocity. With assumptions about how gas orbits the galactic center, these velocity measurements can be converted into distances, allowing three-dimensional mapping of the galaxy's gas distribution. This technique revealed the Milky Way's spiral arm structure in the 1950s, long before optical observations could trace the arms comprehensively. Spiral arms are regions of enhanced gas density where star formation occurs, so mapping where the gas concentrates reveals where the arms are located. The method has limitations. The conversion from velocity to distance requires assuming a rotation curve, the relationship between orbital velocity and distance from the center. If the assumed rotation curve is incorrect, the derived distances will be wrong. Circular orbits must also be assumed, ignoring the fact that gas can have non-circular motions, particularly in regions disturbed by spiral arm dynamics or interactions with the central bar. Infrared observations, particularly in the near-infrared wavelengths between about 1 and 2.5 microns, offer another way to peer through dust. At these wavelengths, dust absorption is reduced by factors of 10 compared to visible light, allowing astronomers to see stars in the galactic plane and central regions that remain hidden at optical wavelengths. The 2-mass survey, completed in 2003, observed the entire sky in near-infrared wavelengths, cataloguing hundreds of millions of stars and galaxies. More recently, the WISE mission and its successor NEOWISE have surveyed the sky at longer infrared wavelengths, revealing cool stars and dust emission invisible to optical telescopes. The Apogee survey, part of the Sloan Digital Sky Survey, uses near-infrared spectroscopy to study stars throughout the galaxy, including regions of the galactic disk and bulge that are too dust-obscured for optical spectroscopy. By targeting red giant stars, which are intrinsically bright and therefore visible to great distances, Apogee has measured detailed chemical abundances for hundreds of thousands of stars across a huge volume of the galaxy. These chemical fingerprints reveal each star's birth environment, allowing astronomers to trace galactic chemical evolution and stellar migration patterns. X-ray observations contribute by revealing the hottest, most energetic phenomena in the galaxy. The supermassive black hole at the galactic center occasionally flares in X-rays when it accretes material. Supernova remnants, the expanding debris from exploded stars, glow brightly in X-rays as their shock waves heat surrounding gas to millions of degrees. Binary systems containing neutron stars or stellar mass black holes produce X-ray emission as they strip gas from companion stars. These high-energy signatures trace different populations and processes than optical or infrared observations, providing complementary information about the galaxy's structure and activity. Astrometry, the precise measurement of stellar positions and motions, has reached extraordinary precision with Gaia. The spacecraft measures not just where stars are at a single moment, but how their positions change over time. These changes have two components. Parallax is the apparent back-and-forth motion caused by Earth's orbit around the Sun, with the amplitude inversely proportional to distance. Proper motion is the star's actual motion across the sky, its velocity perpendicular to our line of sight projected onto the celestial sphere. Measuring both parallax and proper motion for millions of stars allows astronomers to reconstruct their three-dimensional positions and velocities, creating a dynamic map of the galaxy. The power of this approach cannot be overstated. Before Gaia, astronomers had rough distance estimates for perhaps a few thousand stars, decent estimates for a few tens of thousands, and poor or no estimates for the rest. Now we have accurate distances for hundreds of millions of stars and less precise but still useful estimates for over 1 billion. The improvement in data quality is comparable to going from a blurry, pixelated photograph to ultra-high-definition video. Features that were invisible or ambiguous before now stand out clearly. Computer simulations play an increasingly important role in interpreting observations. Modern simulations can model the formation and evolution of an entire galaxy, following hundreds of millions of particles representing stars, gas, and dark matter as they interact gravitationally over billions of years. By comparing simulated galaxies to observations of the Milky Way, astronomers test whether their theoretical understanding of galaxy formation can reproduce what we actually see. These simulations have revealed that galaxy formation is a complex, chaotic process. Galaxies grow through continuous accretion of gas from their surroundings and through mergers with smaller galaxies. Each merger leaves traces in the positions, velocities, and chemical compositions of stars. The Milky Way's structure today reflects its entire history, and by carefully dissecting that structure, astronomers can work backward, reconstructing past events like the collision with Gaia, Sausage, and Enceladus that occurred billions of years ago. Statistical methods tie all these observations together. No single measurement gives a complete picture. Instead, astronomers combine data from multiple surveys, each covering different regions, different stellar populations, different wavelengths. Bayesian inference techniques allow rigorous combination of diverse datasets with their varying uncertainties and selection effects. Machine learning algorithms help classify stars, identify patterns, and extract signals from noisy data. The statistical revolution in astronomy has been as important as the observational advances, enabling sophisticated analyses that would have been impossible just a decade or two ago. One particularly powerful approach involves what astronomers call chemical tagging. Every star's chemical composition reflects the gas cloud from which it formed. Stars born in the same cloud at the same time should have nearly identical chemical fingerprints, with specific patterns of elemental abundances that distinguish them from stars formed elsewhere or at different times. By measuring detailed abundances of dozens of chemical elements for thousands of stars, astronomers can identify groups of stars that likely formed together even if they have since dispersed across the galaxy. This technique has revealed that many stars in the solar neighbourhood, stars we once thought were independent objects with no special relationship to each other, actually formed in common clusters that have long since dissolved. The Sun itself may have siblings, stars born in the same molecular cloud 4.6 billion years ago, now scattered across hundreds or thousands of light years. Finding these siblings would tell us about the Sun's birth environment and the conditions under which the solar system formed. Another technique involves astroseismology, the study of oscillations in stars. Like seismic waves on Earth revealing our planet's internal structure, oscillations in stars reveal their interior properties. The frequencies at which a star oscillates depend on its mass, radius, and internal density profile. By measuring these frequencies through very precise photometry, detecting tiny variations in brightness, astronomers can determine stellar properties with remarkable accuracy. The Kepler spacecraft, designed to find exoplanets, also revolutionized astroseismology, measuring oscillations in thousands of stars and allowing detailed characterization of their fundamental properties. For red giant stars, astroseismology can determine masses accurate to a few percent and ages accurate to 10 or 20%. This is extraordinary for objects tens of thousands of light years away. Knowing ages allows astronomers to date different components of the galaxy, determining when the disk formed, when the bulge assembled, when major merger events occurred. This timeline of galactic evolution provides crucial constraints on theoretical models. The combination of all these techniques, optical and infrared photometry, spectroscopy across multiple wavelengths, astrometry, radio observations, X-ray imaging, astroseismology, computer simulations and advanced statistical analysis gives modern astronomers an unprecedented ability to measure and understand the Milky Way. Each technique has strengths and weaknesses. Each probes different aspects of the galaxy. Together they provide complementary views that, when synthesized, reveal the galaxy's three-dimensional structure, its mass distribution, its chemical evolution, and its dynamical history with a completeness that would have seemed like science fiction just a generation ago. Imagine a wheel made of stars. Not a small wheel, not even a large wheel by any terrestrial standard, but a wheel so colossal that if you could somehow shrink the entire solar system out to Neptune's orbit down to the size of a quarter, the Milky Way's disk would stretch from coast to coast across the United States. This is the scale we are dealing with. This is the structure we inhabit. The stellar disk is what we see when we look at the Milky Way arching across the night sky. From our vantage point inside it, roughly 26,000 light-years from the centre, we see it edge on like looking at a dinner plate from the side rather than from above. The disk appears as that milky band stretching from horizon to horizon because we are looking through the greatest concentration of stars, seeing the accumulated light of billions of distant suns all smeared together into a glowing ribbon. The disk itself is a pancake, flattened by rotation. Gravity pulls everything toward the centre, but the galaxy's spin creates centrifugal force that resists this inward pull. The balance between these forces creates a structure that is wide but thin. Current measurements indicate the disk spans approximately 100,000 light-years in diameter, but its thickness varies dramatically depending on where you measure. Near the spiral arms, where our Sun resides, the disk is roughly 1,000 light-years thick. This might sound substantial, but the ratio of diameter to thickness is about 100 to 1. If the Milky Way were a vinyl record 12 inches across, it would be only about 0.12 inches thick, thinner than most records you could buy. This extreme flatness is a direct consequence of rotation. Just as a pizza chef spinning dough creates a flat, round pie, the rotation of the galaxy has flattened its disk into a thin plane over billions of years. But the disk is not uniform. Astronomers have identified at least two distinct components, a thin disk and a thick disk, each with different properties and histories. The thin disk, where most of the galaxy's current action happens, extends only about 300 to 400 parsecs above and below the galactic plane. For reference, 1 parsec equals 3.26 light-years, so we're talking about a layer roughly 1,000 to 1,300 light-years thick. This thin disk contains the youngest stars, the most vigorous star formation, nearly all the galaxy's gas and dust, and the prominent spiral arm features that give the Milky Way its characteristic pinwheel appearance. Beneath the thin disk, like a foundation supporting a building, lies the thick disk. This component extends roughly 3 times farther above and below the plane, reaching about 3,000 light-years in height. The thick disk contains older stars, populations that formed billions of years ago when the galaxy was younger and more chaotic. These stars have different chemical compositions than thin disk stars, containing fewer heavy elements because they were born before multiple generations of supernovae had enriched the interstellar medium with metals. Their orbits are also more random, less orderly than the neat circular paths followed by younger stars in the thin disk. The spiral arms themselves are among the most striking features of the disk. The Milky Way is classified as a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms emerging from the bar's ends. Current models suggest the galaxy has 4 major spiral arms, 2 primary arms called Scutum Centaurus and Perseus, and 2 secondary arms called Norma and Sagittarius. These arms are not solid structures, they're density waves, regions where stars, gas and dust bunch together temporarily as they orbit the galactic center. Think of spiral arms like traffic jams on a circular highway. The cars, stars, are all moving at different speeds depending on their distance from the center, but certain regions develop higher densities where cars bunch together. These high-density regions rotate around the galaxy at a different speed than the cars themselves. A star might spend a few million years moving through a spiral arm, during which time it is part of that bright, prominent feature, but eventually it emerges from the other side and continues its orbit through less dense regions. The spiral arms persist even though individual stars flow through them, just as a traffic jam can persist in the same location, even though different cars occupy it at different times. The arms are crucial to the galaxy's evolution, because compression in these high-density regions triggers star formation. When a cloud of gas and dust enters a spiral arm, the increased gravitational field compresses it, and portions of the cloud become dense enough to collapse under their own gravity. This collapse ignites nuclear fusion, and new stars are born. This is why spiral arms appear bright and blue in photographs of other galaxies. They are packed with young, hot, massive stars whose short lifespans mean they never drift far from their birthplaces before exploding as supernovae. Our Sun currently resides in a minor spur called the Orion Arm, located between the Perseus and Sagittarius arms. We're not in the middle of a major traffic jam, so to speak, but rather in a smaller local concentration. This position offers some advantages. The intense radiation from massive young stars in the main spiral arms might be hazardous to developing life. Our location in a quieter region may have provided the stability necessary for life on Earth to evolve over billions of years. But even this relatively straightforward picture of a flat disk with spiral arms hides complexities that astronomers have only recently discovered. The disk is not perfectly flat. It warps, bending above and below the ideal plane like a potato chip someone has grabbed by its edges and twisted. The warp becomes pronounced in the outer regions of the disk, beyond about 50,000 light-years from the center, where the gravitational influence of the massive central regions becomes weaker, and tidal forces from nearby satellite galaxies can distort the disk's shape. There is also a subtle but measurable tilt. Recent studies using data from the Gaia spacecraft have revealed that the entire disk appears to be wobbling, possibly in response to gravitational torques from the dark matter halo surrounding the galaxy, or from interactions with infalling dwarf galaxies. The stellar halo, which we will discuss shortly, is tilted about 25 degrees relative to the disk's plane, suggesting complex gravitational dynamics that we're only beginning to understand. The disk rotates, but not like a solid wheel. Different parts rotate at different speeds in a complex pattern that reveals the distribution of mass throughout the galaxy. Near the centre, stars orbit quickly. Moving outward, the rotation speed initially increases, reaches a peak, and then, depending on the measurement techniques used, either levels off or decreases slightly. This rotation curve encodes crucial information about the galaxy's mass distribution, including the invisible dark matter that dominates the galaxy's gravitational field. Measuring this rotation has led to one of the most important discoveries in modern astronomy. Most of the galaxy's mass is not in stars at all. The visible stars, gas and dust account for perhaps 10 to 15% of the total gravitating mass. The rest is dark matter, invisible material that reveals itself only through its gravitational effects. Without dark matter, the outer regions of the galaxy should rotate much more slowly than they actually do, following simple Newtonian mechanics. But they do not. They rotate too fast, held in their orbits by the gravity of something we cannot see. This realization transforms our understanding of the disk's true extent. The visible edge of the stellar disk, where star density drops below detectability, does not mark the end of the galaxy. It marks only the end of the luminous material. The dark matter halo extends far beyond, creating a gravitational well that contains the visible galaxy, like a basketball sitting at the bottom of a trampoline's depression. And as we will discover, recent measurements suggest this dark matter halo may extend to distances that dwarf even the impressive 100,000 light-year span of the visible disk. How many stars are in the Milky Way? It seems like a simple question. Point your telescope at the sky, count the stars, and multiply by however many fields of view it would take to cover the whole galaxy. Easy, right? Except it is not easy at all. It might be one of the most difficult census problems in existence. The challenge begins with the sheer scale of what we are trying to count. On a perfectly dark night far from any city lights, a person with excellent vision might see about 3,000 stars with their naked eye. This represents a minuscule fraction of the galaxy's stellar population, visible only because these particular stars happen to be relatively close to Earth and bright enough for our limited biology to detect. The vast majority of the galaxy's stars are too faint, too distant, or hidden behind clouds of obscuring dust for us to see without technological assistance. Consider what this means in practice. If you observe a patch of sky with a small telescope, you might count a few hundred stars in your field of view. Expand to a larger telescope with greater light-gathering power, and the count jumps to thousands as fainter stars become visible. Use a cutting-edge instrument like those on the Hubble Space Telescope or ground-based observatories equipped with adaptive optics, and individual fields of view reveal tens of thousands of stars, each one a distant sun with its own potentially unique characteristics. But even counting every visible star in every possible direction would not give you the galaxy's total population. The centre of the galaxy is so dense with stars that they blend into an unresolvable glow. Modern instruments can distinguish perhaps 84 million individual stars in the central bulge, an impressive number that represents the result of years of painstaking observation with specialised infrared telescopes that can penetrate the dust. Yet even this massive catalogue captures only the brightest giants in the central regions. Countless fainter stars remain merged into the background glow, individually invisible but collectively contributing to the luminosity we measure. The disk contains thick lanes of dust that block light from stars behind them, creating dark patches in what would otherwise be a continuous blanket of stars. These dust clouds are composed of tiny particles, grains of carbon and silicates with dimensions measuring only microns across. They absorb and scatter blue light preferentially, allowing redder wavelengths to pass through with less obstruction. This selective absorption creates the beautiful dark lanes visible in edge-on images of spiral galaxies, including our own when viewed from within. But it also means that visible light observations dramatically undercount stars in dust-obscured regions. Infrared observations help pierce through the dust, because longer wavelengths are less affected by scattering. The 2024 studies that revised our understanding of the Milky Way's structure relied heavily on near-infrared surveys like apogee, which operates at wavelengths where dust absorption is reduced by factors of 10 or more compared to visible light. This allows astronomers to see stars hidden behind dust clouds, filling in gaps that would otherwise remain invisible. But even infrared light has limits. The thickest dust lanes, particularly in the molecular clouds where new stars are actively forming, remain opaque even at these longer wavelengths. The outer reaches of the galaxy fade into background noise. where distinguishing a distant galaxy star from foreground objects in our own solar system or background galaxies billions of light years away becomes nearly impossible. At distances beyond 100,000 light years, individual stars become so faint that detecting them requires extremely long exposures with the largest telescopes available. The Hubble Space Telescope, for example, can detect individual stars in some nearby galaxies, millions of light years away, but only the brightest supergiants. Regular stars like our Sun become utterly invisible at such distances, lost in the overwhelming background light from billions of unresolved fainter stars. Given these observational challenges, astronomers resort to statistical methods and indirect measurements. The most common approach involves measuring the galaxy's total luminosity, the integrated light from all its stars, and then dividing by the average luminosity of a single star to estimate the total number. But this method immediately confronts a critical question: what is the luminosity of an average star? The Sun produces a luminosity of about 3.8 times 10 to the 26 watts, a number that serves as a convenient unit for stellar astronomy. But the Sun is not average. It is more luminous than the majority of stars in the galaxy, so astronomers resort to cleverer methods. The most common approach involves measuring the galaxy's total mass, and then estimating what fraction of that mass consists of stars. This requires understanding the galaxy's rotation curve, the relationship between distance from the centre and orbital velocity. By observing how fast stars and gas clouds move at various distances, astronomers can calculate the gravitational pull acting on them, which in turn reveals the mass distribution creating that pull. Current mass estimates for the Milky Way cluster around 1.5 trillion solar masses, though measurements range from as low as 800 billion to as high as 4.5 trillion solar masses, depending on the methods used and the assumed age of the galaxy. Most of this mass is dark matter. The stellar component, the actual stars we can see or infer, accounts for only 60 to 80 billion solar masses. This is the mass budget we have to work with when estimating the number of stars, but here the problem becomes subtle. What is the mass of an average star? If you assume all stars are like the Sun, each with one solar mass, you would calculate roughly 60 to 80 billion stars, but the Sun is not an average star. It is actually more massive than most stars in the galaxy. The majority of stars are red dwarfs, cool, dim stars with masses ranging from 0.08 to 0.5 solar masses. These stars are incredibly common, but difficult to detect because they emit so little light. A red dwarf might shine with only 0.01% of the Sun's luminosity, making it essentially invisible at distances greater than a few hundred light years. If red dwarfs dominate the stellar population, as observations of nearby stars suggest they do, then the average stellar mass might be closer to 0.3 or 0.4 solar masses. Using this lower average, the same 60 to 80 billion solar masses of stellar material translates into 150 to 250 billion stars, or even more if red dwarfs are more abundant than current models suggest. Alternatively, astronomers can analyze the integrated light from the galaxy. Different types of stars emit different spectra, unique fingerprints of light that reveal their temperature, composition, and luminosity. By studying the combined spectrum from large regions of the galaxy, scientists can estimate the mix of stellar types present, and from that infer the total stellar population. This method has its own uncertainties because it depends on assumptions about the galaxy's star formation history and the initial mass function, the distribution of masses for newly formed stars. Recent estimates converge on a range of 100 billion to 400 billion stars for the Milky Way, with 200 billion often cited as a reasonable middle estimate. This represents an enormous spread, a factor of 4 uncertainty in what should be a fundamental property of our home galaxy. The uncertainty reflects the genuine difficulty of the measurement and the compounding effects of multiple assumptions that must be made along the way. The Gaia spacecraft, launched by the European Space Agency in 2013, has revolutionized our ability to count stars. Gaia's mission is to measure the positions, distances, and motions of more than 1 billion stars with unprecedented precision. By 2024, Gaia has catalogued 1.7 billion stars, providing accurate three-dimensional positions and velocities for each one. This represents less than 1% of the galaxy's total stellar population, but it is by far the most comprehensive and accurate stellar census ever conducted. Gaia's data has expanded the measurable volume of space by a factor of 100 in radius and a factor of 1,000 in precision compared to pre-Gaia measurements. Astronomers can now map the structure of the disk, trace the spiral arms, identify streams of stars torn from disrupted dwarf galaxies, and measure the subtle wobbles and warps in the galactic disk. All of this information feeds into models that attempt to extrapolate from Gaia's billion stars to the galaxy's total population. But Gaia has its limits. It struggles to see the faintest stars, the most distant stars, and stars in the crowded central regions where the stellar density is so high that individual stars blend together. Even Gaia cannot provide a complete census. What it provides instead is a representative sample, a statistically significant slice of the galactic population that astronomers can study in detail and then use to infer properties of the whole. One fascinating result from Gaia's data involves the stellar mass of the Milky Way. A 2024 study using Gaia measurements revised the estimate of the galaxy's total stellar mass downward to about 26 billion solar masses, significantly lower than previous estimates. This suggests the Milky Way may actually be less massive in stars than previously thought, which has implications for how we understand the galaxy's formation and evolution. A less massive stellar component means dark matter dominates even more than we realized, and it places the Milky Way closer to the average mass for spiral galaxies, rather than making it an unusually massive example. The composition of the stellar population also matters. The Milky Way contains an extraordinary diversity of stars. The most massive stars, blue supergiants burning hydrogen at prodigious rates, can have masses 100 times that of the Sun, and luminosities 1,000,000 times greater. But these stellar behemoths are exceedingly rare and short-lived, exhausting their fuel in just a few million years before exploding as supernovae. At the other extreme, the least massive red dwarfs, barely massive enough to sustain hydrogen fusion, can burn for trillions of years, far longer than the current age of the universe. In between these extremes lie all the other stellar types: yellow dwarfs like our Sun, orange dwarfs, white dwarfs that are the stellar corpses left behind when Sun-like stars die. Neutron stars crush to incredible densities by supernova explosions, and stellar mass black holes, the collapsed cores of the most massive stars. Each category contributes differently to the galaxy's total mass, total light, and chemical enrichment. The interplay between these different stellar populations drives the galaxy's evolution, creating the heavy elements necessary for planets and life, while also sculpting the interstellar medium through stellar winds and supernova explosions. Understanding the stellar census is not just an academic exercise in accounting. The number of stars, their types, and their distribution tell us about the galaxy's history. When did star formation begin? How has the star formation rate changed over time? Where in the galaxy have most stars formed? These questions connect directly to understanding how galaxies in general form and evolve, making the Milky Way a crucial laboratory for testing theories about cosmic structure formation. So while we cannot give a precise answer to the question, how many stars are in the Milky Way, we can say with confidence that the number falls somewhere between 100 billion and 400 billion, with ongoing observations continually refining this range. Each star is a sun, potentially surrounded by its own family of planets, each representing a possible site where chemistry and physics might give rise to complexity, perhaps even to life. The sheer scale of the numbers staggers the imagination and reminds us that even in our own cosmic neighbourhood, we have barely begun to explore the full diversity of worlds and phenomena waiting to be discovered. Everything we have discussed so far, the entire visible Milky Way with its 100,000 light-year disk and hundreds of billions of stars, represents less than 10% of the galaxy's total mass. The rest, the overwhelming majority, is dark matter, invisible material that reveals itself only through gravity. And recent measurements suggest this dark matter extends far beyond the visible disk, creating a halo that may stretch nearly 2 million light-years from the galactic centre. This is where our understanding of the galaxy's true size becomes both more certain and more speculative at the same time. The dark matter halo dominates the galaxy's gravitational field. Without it, the galaxy as we know it could not exist. The visible stars and gas would not have enough gravity to hold themselves together in their current configuration. Stars in the outer regions orbit too fast to be bound solely by the mass of visible matter. They should be flung into intergalactic space, yet they are not. something massive and invisible is holding them in their orbits. That something is the dark matter halo, a roughly spherical distribution of matter that envelops the entire visible galaxy like a cloud. We cannot see it. We cannot detect it with any electromagnetic radiation, no light, radio waves, X-rays, or any other form of photon. Dark matter does not emit, absorb, or reflect electromagnetic energy. It is transparent to light, allowing photons to pass through it, undisturbed. The only way we know it exists is by measuring its gravitational effects on things we can see. The story of dark matter's discovery is itself fascinating and deserves elaboration because it fundamentally changed how astronomers think about galaxies and the universe as a whole. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a group of over 1,000 galaxies bound together by their mutual gravity. By measuring the velocities of individual galaxies within the cluster, using Doppler shifts of their spectral lines, Zwicky could calculate the total kinetic energy of the cluster. The virial theorem, a fundamental result from classical mechanics, relates the total kinetic energy of a gravitationally bound system to its total gravitational potential energy, which in turn depends on the total mass. When Zwicky performed this calculation, he found something deeply troubling. The galaxies were moving much faster than the visible mass of the cluster could account for. There was nowhere near enough gravitating matter to explain their velocities. Either Newtonian mechanics was wrong on these scales, which seemed unlikely given its success everywhere else, or the cluster contained far more mass than could be seen. Zwicky called this unseen component dunkle materie, or dark matter. His contemporaries largely dismissed the finding as either an observational error or a peculiarity of that particular cluster. The evidence became undeniable in the 1970s when American astronomer Vera Rubin, working with Kent Ford, measured rotation curves for spiral galaxies. A galaxy's rotation curve shows how fast stars and gas orbit at different distances from the centre. Simple Newtonian mechanics predicts that once you move beyond the bulk of the visible matter, the rotation speed should decline, following the same pattern that governs planetary orbits. The farther from the mass concentration, the slower the orbit. This is why the outer planets in our solar system orbit much more slowly than the inner planets. But Rubin and Ford found that galaxy rotation curves do not decline at large radii. Instead, they remain flat or even increase slightly, with stars at the outer edges orbiting just as fast or faster than stars closer to the centre. This flatness implies that mass continues to exist at large radii, even where no stars or gas are visible. The only explanation that fits the observations is a massive halo of invisible matter extending far beyond the visible disk, its gravity pulling on the outer stars and keeping them in rapid orbits. Rubin measured this effect in galaxy after galaxy, finding the same pattern repeatedly. It was not a fluke or an error, it was a fundamental property of spiral galaxies, and by extension, it must be true for the Milky Way as well. We could not easily measure our own galaxy's rotation curve from inside it, but there was no reason to think we were special. If other spiral galaxies had dark matter halos, we must too. Those effects are substantial. Measurements using globular clusters as tracers, ancient spherical collections of stars that orbit the galaxy in elongated paths, indicate that the inner regions of the dark matter halo contain roughly 137 billion solar masses of dark matter within 65,000 light-years of the centre. This is already more than twice the mass of all the galaxy's visible stars, and this is just the inner halo. The total mass of dark matter in the entire Milky Way system may be 10 to 15 times the mass of all visible matter. The method of using globular clusters as tracers deserves explanation, because it represents one of the most elegant techniques in observational astronomy. Globular clusters are ideal test particles for measuring the galaxy's gravitational potential because they are simple, well-understood systems. Each cluster is an isolated, gravitationally bound sphere of hundreds of thousands to millions of stars. The stars within a cluster orbit their common centre of mass, and the cluster as a whole orbits the galaxy following a path determined solely by the galaxy's gravitational field. Unlike gas or young stars, which can be affected by magnetic fields, radiation pressure or other non-gravitational forces, globular clusters respond only to gravity. By measuring the three-dimensional positions and velocities of many globular clusters, astronomers can reconstruct the gravitational potential that must exist to produce their observed orbits, This is essentially an inverse problem. Given the orbits, figure out the distribution of mass. The technique requires accurate measurements of cluster distances, which come from observations of their constituent stars, and accurate measurements of their velocities, which come from Doppler shifts combined with proper motion measurements showing how the clusters move across the sky over time. The Gaia spacecraft has revolutionized this field by providing unprecedented proper motion measurements for globular clusters out to distances exceeding 100,000 light-years. Combined with radial velocity measurements from ground-based spectroscopy and complementary observations from the Hubble Space Telescope for more distant clusters, astronomers now have 6-dimensional phase space information for more than 150 clusters. This allows detailed modelling of the dark matter distribution with error bars that have shrunk dramatically compared to pre-Gaia estimates. Recent simulations and observations suggest the dark matter halo extends to a radius of at least 300,000 parsecs, or roughly 980,000 light-years. Some estimates push this boundary even farther, to 613 kiloparsecs, or about 2 million light-years. At this distance, the halo's density has dropped to nearly nothing, but its gravitational influence still reaches inward, affecting the motions of satellites like the Large and Small Magellanic Clouds, and helping to bind the local group of galaxies together. The local group is the collection of galaxies gravitationally associated with the Milky Way, including Andromeda, the Triangulum galaxy, and dozens of smaller dwarf galaxies. The total extent of the local group is about 10 million light-years, and the Milky Way's dark matter halo occupies a significant fraction of this volume. The boundary between where the Milky Way's halo ends and Andromeda's halo begins is not sharp, but rather a transition zone where the gravitational influence of both galaxies becomes comparable. Defining the exact edge of the dark matter halo is difficult because the density does not drop to zero at any specific radius. Instead, it fades gradually, becoming more and more diffuse until it merges with the even lower density of intergalactic space and the halos of neighbouring galaxies. Astronomers typically define the halo's edge using the virial radius, the distance within which the halo's average density is about 200 times the critical density of the universe. The critical density is the average matter density needed to make the universe's expansion eventually halt, a value determined by the Hubble constant and fundamental constants of physics. Using this definition, recent studies in 2020 predicted the Milky Way's dark matter halo extends to 292 kiloparsecs plus or minus 61 kiloparsecs, translating to a diameter of about 1.9 million light-years. This is an astounding number. It means the Milky Way, in its full extent including its dark matter component, is nearly 20 times larger in diameter than the visible spiral disk that Harlow Shapley measured. It transforms our conception of what the galaxy actually is. We think of the Milky Way as that beautiful spiral of stars we see in long exposure photographs, but in reality, that spiral is just the bright centre of a much larger structure, a massive sphere of invisible matter that extends into the darkness far beyond where any stars shine. The visible galaxy is like a glowing ember at the heart of a vast cold cloud. The ember provides the light, but the cloud provides most of the mass and defines the system's true extent. The shape of the dark matter halo has also proven surprising. For decades, astronomers assumed it was roughly spherical, a simple ball of dark matter centered on the galaxy. Recent data from Gaia and other surveys suggest this is not quite right. The halo appears to be triaxial, meaning it is elongated in certain directions like a football rather than a perfect sphere. Moreover, it is tilted relative to the galactic disk, its axis pointing in a different direction than the disk's axis of rotation. This tilt likely resulted from the galaxy's chaotic assembly history. The Milky Way formed through the merger and accretion of many smaller galaxies over billions of years. Each merger brought not only stars but also dark matter, and the cumulative effect of all these collisions created a halo with complex structure and orientation. The tilt survived because dark matter, which interacts only through gravity, does not experience friction or collisions that would cause it to settle into a rotating disk like normal matter does. Once tilted, the dark matter halo has no mechanism to align itself with the visible disk. One particularly important merger involved a dwarf galaxy astronomers whimsically call Gaia Sausage Enceladus, or GSE for short. This galaxy collided with the Milky Way between 7 and 10 billion years ago. The impact was catastrophic. The dwarf galaxy was torn apart, its stars scattered into a vast halo around the Milky Way. But the collision also affected the dark matter distribution, contributing to the halo's current shape and tilt. The stars from GSE form a prominent component of the Milky Way's stellar halo, and their distinctive chemistry and kinematics allow astronomers to identify them even billions of years after the merger. The stellar halo itself deserves mention. This is the component of visible matter that extends beyond the disk, a diffuse sphere of old stars surrounding the galaxy. The stellar halo contains only about 1% of the galaxy's total stellar mass, but it extends hundreds of thousands of light-years from the galactic center, overlapping with the dark matter halo. Most stellar halo stars are ancient, metal-poor objects that formed in the early universe, either in the first generations of star formation within the proto-Milky Way or in the dwarf galaxies that later merged with it. Globular clusters, those dense spherical collections of hundreds of thousands to millions of stars, are part of the stellar halo. The Milky Way contains more than 150 known globular clusters, though dust and gas in the galactic disk likely obscure additional clusters from our view. These clusters orbit the galaxy on highly elliptical paths, plunging through the disk plane before swinging back out to great distances. They serve as excellent tracers of the galaxy's gravitational potential, because their orbits respond only to gravity, unaffected by the complex gas dynamics and star formation processes that complicate the motions of disk stars. By measuring the velocities of globular clusters at various distances from the galactic center, astronomers can map the gravitational field and thereby infer the distribution of mass, both visible and dark. Studies using data from both Gaia and the Hubble Space Telescope have measured the three-dimensional motions of clusters out to distances exceeding 100,000 light-years, providing the most accurate mass measurements yet for the inner and intermediate regions of the dark matter halo. The total mass of the Milky Way within 65,000 light-years is estimated at about 191 billion solar masses, of which 137 billion is dark matter. Within 130,000 light-years, the total mass rises to approximately 900 billion solar masses. And if we include the entire dark matter halo out to the virial radius, the total mass may reach 1.5 trillion solar masses or more, depending on the exact assumptions made about the halo's density profile and extent. These numbers place the Milky Way squarely in the middle of the mass range for spiral galaxies. The lightest galaxies weigh in at around 1 billion solar masses, while the most massive can reach 30 trillion solar masses. At 1.5 trillion solar masses, the Milky Way is substantial but not exceptional, a fairly typical example of a large spiral galaxy. This is actually reassuring from a cosmological perspective. If the Milky Way were highly unusual, studying it might not tell us much about galaxies in general. But because it appears to be relatively normal, lessons learned from detailed studies of the Milky Way can be applied to understanding other galaxies throughout the universe. The dark matter halo is not uniform. Simulations suggest it should contain substructures, clumps and streams of dark matter that have not yet fully merged into a smooth distribution. These substructures arise from the same hierarchical assembly process that built the galaxy: smaller dark matter halos from satellite galaxies and from primordial fluctuations in the early universe. If these clumps exist, they might be detectable through their gravitational effects on stellar streams, narrow ribbons of stars stripped from globular clusters as they orbit through the galaxy. The nature of dark matter itself remains one of the greatest unsolved mysteries in physics. We know it exists. We can measure its mass and map its distribution. We know it does not interact with light, and that it accounts for about 85% of all matter in the universe. But we do not know what it is made of. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical subatomic particles that have mass but rarely interact with normal matter. Other proposals involve axions, sterile neutrinos, or more exotic possibilities. Despite decades of searching, no experiment has yet directly detected a dark matter particle. Understanding dark matter is crucial to understanding the true size and nature of the Milky Way. The dark matter halo is the scaffolding on which the visible galaxy hangs. It determined where and how the disk formed. It regulates the galaxy's rotation. It binds satellite galaxies into orbits around the Milky Way. and it extends the galaxy's reach far beyond the visible stars, making the Milky Way a structure nearly 2 million light-years across rather than merely 100,000. This invisible giant, this dark ocean in which our visible galaxy floats, changes everything about how we understand our cosmic home. We are not just embedded in a disk of stars, we are embedded in a massive halo of mysterious matter that outweighs everything we can see by a factor of 10 or more. And that realization, as uncomfortable as it may be, represents one of the most profound discoveries in the history of astronomy. In December 2013, a spacecraft no larger than a small car launched from French Guiana aboard a Soyuz rocket. Its destination was not another planet or moon, but rather a special point in space called L2, located about 1.5 million kilometers from Earth on the side facing away from the Sun. At this location, the gravitational pulls of the Sun and Earth balance perfectly, allowing a spacecraft to maintain a stable position with minimal fuel expenditure. The spacecraft was Gaia, and its mission would transform our understanding of the Milky Way. Gaia carries the largest digital camera ever built for a space mission, with a resolution of nearly 1 billion pixels spread across 106 individual CCD detectors. The detectors are arranged in a sophisticated configuration that allows the spacecraft to simultaneously measure positions, colours, and brightnesses of stars as they drift across its field of view. The spacecraft slowly rotates, completing one full rotation every 6 hours, scanning the entire sky in a systematic pattern that ensures every star is observed multiple times from different angles over the mission's lifetime. The spacecraft also carries 2 telescopes, each with a 1.45 meter by 0.5 meter primary mirror, configured to look in different directions separated by precisely 106.5 degrees. This dual telescope arrangement is crucial for Gaia's primary science goal. As the spacecraft rotates, stars drift through the fields of view of both telescopes at different times. By comparing when a star passes through one telescope's field versus when it passes through the other, Gaia can determine the star's position with extraordinary precision. The separation between telescopes creates a large baseline for triangulation, essentially giving Gaia 2 widely separated eyes for measuring stellar positions. Additionally, Gaia carries sophisticated instruments designed to measure positions, distances, and motions of stars with unprecedented precision. The spacecraft includes a radial velocity spectrometer that measures Doppler shifts to determine how far stars are moving toward or away from us. It has photometric instruments that measure star colors in multiple wavelength bands, providing information about stellar temperatures and compositions. Every component of the system is designed to work together, creating a comprehensive survey that maps not just where stars are, but how they are moving through 3-dimensional space. The goal is audacious: to map the 3-dimensional positions and velocities of more than 1 billion stars, creating a dynamic census of the Milky Way that captures not just where stars are, but where they are going. To understand why this is revolutionary, consider what astronomical measurements looked like before Gaia. For most stars, astronomers knew their position on the sky, essentially their coordinates in right ascension and declination, the astronomical equivalent of longitude and latitude. They might have a rough estimate of the star's distance, often uncertain by 20 or 30% or more. And for many stars, they had no reliable distance measurement at all, just an educated guess based on the star's brightness and spectral type. This meant that most of our 3-dimensional maps of the galaxy were built on shaky foundations. You might know that 2 stars appeared close together on the sky, but you could not be sure if they were actually neighbours in space, or if one was much farther away than the other, coincidentally aligned along our line of sight. The spiral arms were known to exist from radio observations of hydrogen gas, but tracing their exact shape and extent required making assumptions about which stars belonged to which arms. The precision of Gaia's measurements is difficult to overstate. For the brightest stars, Gaia measures positions accurate to about 7 microarc seconds. To put this in perspective, 1 arcsecond is 1 to 3,600th of a degree. A microarcsecond is 1 millionth of an arcsecond. Gaia's precision is equivalent to measuring the width of a human hair from a distance of 1,000 kilometers, or detecting the position of a coin on the surface of the moon as seen from Earth. This is not hyperbole. These are the actual scales involved. This level of precision is necessary because stellar parallaxes, the apparent shifts in position as Earth orbits the Sun, are incredibly small even for nearby stars. The closest star system to Earth, Alpha Centauri at 437 light-years away, has a parallax of only 0.75 arc-seconds. Stars at 100 light-years have parallaxes of 0.03 arc-seconds. At 1,000 light-years, the parallax drops to 0.003 arc-seconds or 3,000 micro-arc-seconds. Gaia can reliably measure parallaxes down to about 20 micro-arc-seconds, allowing distance determinations accurate to about 10% for stars out to 10,000 light-years. For comparison, the pre-Gaia Hipparcos mission, which represented the previous state-of-the-art, could measure parallaxes down to about 1,000 micro-arc-seconds, limiting high-accuracy distances to a few hundred light-years. Gaia changed all of this. The spacecraft measures each target star multiple times over the course of its mission, watching how the star's position changes as Earth and Gaia orbit the Sun. This changing perspective creates a tiny apparent shift in the star's position called parallax, the same effect that makes your finger appear to jump when you alternately close your left and right eyes. The size of the parallax shift depends on the star's distance. Closer stars shift more, distant stars shift less. By measuring this shift with extreme precision, Gaia determines distances accurate to within a few percent for stars up to thousands of light-years away. The numbers are staggering. Gaia has measured positions of 1.8 billion stars, more stars than any previous astronomical survey by orders of magnitude. For 1.5 billion of them, it has determined accurate parallaxes and therefore distances. For hundreds of millions, it has also measured the star's velocity across the sky, how fast it is moving in directions perpendicular to our line of sight, captured as proper motion measured in milliseconds per year. Combining this with spectroscopic measurements that give radial velocities, the motion toward or away from us, astronomers can reconstruct each star's full three-dimensional velocity through space. The catalogue is so large that simply downloading and working with the data presents computational challenges. The third Gaia data release, published in June 2022, contained information on 1.8 billion sources with a total data volume of several terabytes. Individual astronomers cannot casually browse this dataset. Specialized software tools and database systems are required to query and analyze subsets of the data relevant to specific scientific questions. Yet despite these challenges, the Gaia catalogue has become the foundation for virtually all modern research on the structure and dynamics of the Milky Way. This has expanded the volume of space that astronomers can map with high precision by a factor of 100 in radius and a factor of 1,000 in precision compared to pre-Gaia measurements. It is not an exaggeration to say that Gaia has revolutionized galactic astronomy more than any single mission since Hubble. The data it has produced will occupy astronomers for decades, with new discoveries emerging regularly as researchers develop new ways to analyze the enormous dataset and extract information about stellar populations, galactic structure, and the dynamics of the Milky Way system. Early results from Gaia's first data releases have already yielded profound discoveries. The spacecraft detected a wobbling motion in the galactic disk, possibly caused by gravitational torques from the tilted dark matter halo or from interactions with satellite galaxies. It revealed the complex stream of stars torn from the Gaia, Sausage, and Enceladus dwarf galaxy, allowing astronomers to reconstruct the details of this ancient merger. It discovered previously unknown stellar streams, subtle traces of disrupted globular clusters and dwarf galaxies. Gaia has also revealed the stellar halo's true shape. For decades, astronomers assumed the halo was roughly spherical. Gaia data, combined with observations from ground-based surveys, showed that the halo is actually traxial and tilted about 25 degrees relative to the galactic disk. This finding provides strong support for the theory that the halo formed primarily through the merger of the GSE dwarf galaxy, which approached the Milky Way at an angle rather than head-on. Perhaps most importantly for understanding the galaxy's size, Gaia has provided the data needed to measure the galaxy's rotation curve with unprecedented accuracy, extending measurements out to 100,000 light-years from the center. These measurements reveal subtle features in how the rotation velocity changes with distance, features that constrain models of the mass distribution, including the dark matter halo. Recent studies have found that the rotation curve decreases at large distances, dropping off more quickly than some previous models predicted. This decline suggests the dark matter halo may be less massive than earlier estimates, though the exact interpretation remains debated. One surprising result from Gaia involves hypervelocity stars, objects moving so fast that they will eventually escape the galaxy's gravity entirely. Gaia has identified hundreds of these stars, which were likely accelerated to their extreme speeds by close encounters with the supermassive black hole at the galactic center, or by supernova explosions in binary star systems. Studying their trajectories helps astronomers understand the galaxy's gravitational potential and test whether the Milky Way's mass is sufficient to retain or lose these high-velocity objects. Gaia has also revolutionized our understanding of stellar populations and the galaxy's chemical evolution. The spacecraft's instruments measure not just positions and motions, but also the colors and brightnesses of stars, which encode information about their temperatures, ages, and chemical compositions. By combining Gaia data with ground-based spectroscopic surveys like APOG, which measures detailed chemical abundances for hundreds of thousands of stars, astronomers have been able to trace how the galaxy's chemistry has changed over time and how it varies from the inner to outer regions. The chemical gradients revealed by these studies tell a story of inside-out formation, where the inner galaxy formed first and the disk gradually built outward over billions of years. They show that different components of the galaxy, the thin disk, thick disk, and halo, have distinct chemical signatures reflecting their different formation histories, and they reveal that the galaxy has not been quietly evolving in isolation, but has been continually perturbed by mergers and interactions with satellite galaxies. Another crucial contribution from Gaia involves the census of the galactic bulge, the dense concentration of stars at the center. The bulge is difficult to study because dust in the galactic disk obscures much of it at optical wavelengths. But Gaia's ability to measure stars in multiple wavelengths, combined with infrared surveys that can penetrate the dust, has revealed that the bulge is not a simple spherical structure, but rather has a bar-like shape, elongated in certain directions. This bar rotates, and its gravitational influence affects the orbits of stars throughout the inner galaxy. The ongoing Gaia mission, expected to continue collecting data through at least 2025, will further refine these measurements. Each additional data release includes more stars, more accurate parallaxes, and extended coverage to greater distances. The third data release, published in 2022, included detailed information for nearly 2 billion objects. Future releases will push even farther, mapping the galaxy's structure to unprecedented depths. But Gaia has limits. It can see only to about 30,000 light-years with high precision for most stars, roughly to the distance of the galactic center from our position. Beyond that, parallax measurements become increasingly uncertain because the shifts become too small to measure reliably. For the most distant stars in the halo or in satellite galaxies, Gaia provides positions but not accurate distances. Understanding the galaxy's full extent still requires combining Gaia data with other techniques. Nevertheless, the impact of Gaia on our understanding of the Milky Way's size and structure cannot be overstated. Before Gaia, we had rough maps based on incomplete data and many assumptions. After Gaia, we have precise three-dimensional measurements for 1 billion stars, a transformational dataset that has already answered old questions and raised new ones. The revolution in galactic astronomy is happening now, and at its center sits a spacecraft barely larger than a refrigerator, quietly measuring starlight from its vantage point 1 million miles from Earth. In June 2024, a team of astronomers led by Jianwei Lian of Yunnan University published a paper that would shake the foundations of how we understand the Milky Way's size. Using data from the APOG spectroscopic survey, combined with Gaia's parallax measurements, they had reconstructed the galaxy's surface brightness profile across an unprecedented radial range, from the very center out to 55,000 light-years. What they found challenged decades of assumptions about the galaxy's structure. The traditional way of measuring a galaxy's size involves fitting an exponential profile to its disk. This assumes the brightness drops off smoothly and predictably as you move outward from the center, following a mathematical function where brightness decreases by the same factor for each unit of distance. For the Milky Way, this method typically yielded a scale length of about 2.6 kiloparsecs, or roughly 8,500 light-years. Using this scale length and various models of the disk's structure, astronomers calculated a half-light radius. the radius containing half of the galaxy's total light, of about 3.4 kiloparsecs, or roughly 11,000 light-years. This number always seemed small. It placed the Milky Way among the most compact galaxies when compared to similar mass spiral galaxies observed in the nearby universe. The Milky Way appeared to be an outlier, unusually dense for its mass. But this result depended entirely on the assumption that the disk followed a simple exponential profile. Lian's team threw out that assumption. Instead of fitting a predetermined mathematical function to the data, they reconstructed the actual surface brightness profile directly from observations of individual stars. They used chemical abundances to separate stars by age, creating separate profiles for young and old stellar populations. They carefully corrected for the selection function of the surveys, accounting for which stars were likely to be observed and which were likely to be missed. The result was a non-parametric surface brightness profile, a measurement of how the galaxy's brightness actually changes with radius, regardless of whether it matches theoretical expectations. What they found was striking. The galaxy does not follow a single exponential profile. Instead, it shows a broken profile with distinct regions. Between about 11,000 and 24,000 light-years from the centre, the surface brightness is nearly flat, not dropping off as quickly as an exponential profile would predict. Beyond 24,000 light-years, the brightness does decline, but the transition is sharp rather than smooth. This broken profile dramatically changes the calculated half-light radius. Instead of 3.4 kiloparsecs, the new measurement yields 5.75 kiloparsecs, or roughly 18,750 light-years. This is 1.7 times larger than the traditional estimate. The difference might not sound huge in absolute terms, but it transforms the Milky Way's standing among other galaxies. With this larger half-light radius, the Milky Way is no longer an unusually compact galaxy. It is perfectly consistent with other disk galaxies of similar mass. The galaxy is not an outlier, it is typical. This revised size estimate comes with important caveats. The half-light radius measures where half the total light originates, which is not the same as the physical extent of the stellar disk. Stars exist well beyond the half-light radius, gradually thinning out until they become too sparse to detect. The visible disk of stars almost certainly extends to at least 65,000 light-years, and possibly to 100,000 light-years or more, though the outer regions are extremely faint and difficult to observe. Recent studies have found evidence for disk stars at distances of 85,000 to 103,000 light-years from the galactic centre, significantly farther than the previously assumed edge at 40,000 to 70,000 light-years. If confirmed, this would mean the stellar disk is considerably more extended than earlier models suggested. The disk does not have a sharp edge, rather it fades gradually, making the definition of size inherently ambiguous. Another 2024 study took a different approach to measuring the galaxy's stellar mass, arriving at a surprisingly low estimate. By reconstructing the three-dimensional mass density distribution from Gaia data and apogee observations, accounting for both living stars and stellar remnants like white dwarfs, neutron stars and black holes, the researchers calculated a total stellar mass of only about 26 billion solar masses. This is significantly lower than previous estimates, which often range from 40 to 80 billion solar masses. A lower stellar mass has profound implications. It means dark matter dominates the galaxy's mass budget even more than previously thought. Within any given radius, a larger fraction of the mass is invisible. This affects our understanding of the galaxy's formation history, its star formation efficiency, and how it compares to other galaxies. It also influences estimates of how many stars the galaxy contains, though the exact number depends on assumptions about the mass distribution of stars. These new measurements highlight a crucial point. Defining the size of the Milky Way is not straightforward. Different definitions lead to different numbers. If you measure the half-light radius, you get about 18,750 light-years. If you measure the radius at which the stellar disk's surface brightness drops below a certain threshold, you might get 50,000 light-years. If you trace the disk out to where individual stars become undetectable, you reach 100,000 light-years. And if you include the dark matter halo, the galaxy extends to nearly 1 million light-years or even 2 million light-years depending on where you draw the boundary. This is not unusual. All galaxies have this property. They do not have sharp edges, They fade into the background, transitioning gradually from regions dominated by the galaxy's gravity and stellar population to intergalactic space. The chosen definition of size reflects what aspect of the galaxy you're trying to capture. Are you interested in where most of the stars are? That is the half-light radius. Are you interested in the maximum extent of the stellar disk? That is the outer edge measurement. Are you interested in the gravitational reach of the galaxy? That is the virial radius of the dark matter halo. Each measurement is valid for its purpose, but they answer different questions. The key insight from the 2024 studies is that the Milky Way is larger and less massive in stars than previous models indicated, making it a more typical galaxy rather than an unusually compact one. This has ripple effect throughout our understanding of galactic evolution and the relationship between visible matter and dark matter in spiral galaxies. The revised measurements also affect estimates of the galaxy's integrated properties, like its total stellar metallicity and its star formation history. A more extended disk with a larger half-light radius means the density of stars at any given radius is lower than previously thought, which changes how we interpret chemical abundance gradients and age distributions. The galaxy's structure is more complex than simple models suggested, with different regions having different formation timescales and enrichment histories. These findings exemplify how our understanding of the Milky Way continues to evolve even for seemingly basic properties like size and mass. Each new survey, each advance in instrumentation, each refinement in analysis techniques brings us closer to the truth. But the galaxy remains elusive, revealing its secrets slowly and sometimes contradicting our expectations. The Milky Way is not a static object to be measured once and filed away. It is a dynamic, complex system whose full nature we are only beginning to grasp. If we are to truly understand the Milky Way's size and structure, we must examine its components individually, each contributing to the overall architecture in distinct ways. Think of the galaxy as a city, a three-dimensional metropolis of stars where different districts have different characters, different ages, and different roles in the city's life. At the very heart lies the nucleus, the galactic downtown, a region only about 400 light-years across, but containing roughly 10 million stars packed into a volume that would fit between Earth and a star just a few hundred light-years away. This is not the suburbs. This is not a neighbourhood where you might go for peace and quiet. The stellar density here reaches levels found nowhere else in the galaxy, with stars separated by distances measured in light weeks rather than light years. Collisions are rare even here because stars are point-like objects despite their immense sizes, but close encounters are common enough to affect stellar orbits significantly. The nucleus harbours Sagittarius A, the galaxy's central supermassive black hole. With a mass of roughly 4.3 million times that of the Sun, this monster lurks at the exact centre of the galactic coordinate system, the point around which everything else rotates. Despite its enormous mass, Sagittarius A is relatively quiet compared to the supermassive black holes in some other galaxies. It consumes material only sporadically, occasionally flaring in X-rays when a wayward gas cloud or stellar remnant strays too close and gets shredded by tidal forces. The black hole's event horizon, the point of no return beyond which nothing can escape, spans only about 25 million kilometres, roughly 1/6 the distance from Earth to the Sun. This makes it tiny on astronomical scales, invisible to direct observation except for the radio emissions from the accretion disk of hot gas swirling around it. The Event Horizon Telescope collaboration famously imaged this region in 2022, revealing the structure of the immediate environment around the black hole. Surrounding the nucleus is the central bulge, a dense spheroidal swarm of stars extending about 10,000 light-years from the centre. The bulge contains primarily old stars, populations that formed billions of years ago when the galaxy was young. The metallicity of bulge stars varies, with some showing the low metal content expected of ancient objects, while others have surprisingly high abundances of heavy elements, suggesting complex formation and enrichment histories. The bulge is not perfectly spherical. Observations in the infrared, which can penetrate the dust obscuring the galactic centre, reveal that the bulge has a bar-like structure, elongated in certain directions. This bar rotates, completing one rotation every few 100 million years. The bar's gravitational influence extends throughout the inner galaxy, affecting the orbits of stars and gas clouds and likely playing a role in funneling material toward the central black hole. Moving outward from the bulge, we encounter the disk, the flat, rotating structure that defines the galaxy's characteristic spiral shape. But the disk is not a monolithic entity. It consists of at least two distinct components, the thin disk and the thick disk, each with different properties. The thin disk, extending about 1,000 to 1,300 light-years above and below the midplane, is where most of the galaxy's current activity occurs. This is the site of ongoing star formation, where giant molecular clouds collapse under their own gravity to birth new stars. The thin disk contains the youngest stellar populations, objects that formed within the last few billion years, and in many cases within the last few million years. These young stars are rich in heavy elements, metals forged in the nuclear furnaces of previous stellar generations and dispersed into space by supernova explosions. The spiral arms carved into the thin disk are density waves, regions where stars, gas and dust temporarily concentrate as they orbit the galactic centre. 4 major arms have been identified: Scutum Centaurus, Perseus, Norma and Sagittarius. These arms wind outward from the central bar in a logarithmic spiral pattern with a pitch angle of about 12 degrees, meaning they are gently curved rather than tightly wound. The arms are not static, they rotate, but at a different speed than the stars themselves. A star might spend a few million years moving through an arm, during which it is part of that bright, prominent feature, but it then emerges from the other side and continues its orbit through the less dense inter-arm regions. The density enhancement in the arms is modest, only about 10 to 20% higher than the surrounding disk, but this is enough to trigger star formation and make the arms visually prominent. Beneath the thin disk lies the thick disk, extending about 3,000 light-years above and below the plane. The thick disk stars are older, with ages ranging from 8 to 12 billion years. They formed early in the galaxy's history, possibly during a more chaotic period when mergers and interactions were common. Their orbits are less circular and more randomly oriented than thin disk stars, suggesting they were heated, their orbits stirred by gravitational perturbations from satellite galaxies or by the galaxy's own evolving potential. The thick disk contains about 5% of the total disk stellar mass, making it a minor component in terms of mass but an important one for understanding the galaxy's history. The chemical composition of thick disk stars differs from thin disk stars, showing lower overall metallicity and different abundance patterns that reflect the conditions under which they formed. These chemical signatures allow astronomers to identify thick disk stars and trace the history of chemical enrichment in the early galaxy. Surrounding and permeating the disk components is the stellar halo, a diffuse sphere of old stars extending hundreds of thousands of light-years from the galactic centre. The halo contains only about 1% of the galaxy's total stellar mass, but it occupies a much larger volume than the disk. Halo stars are ancient, with ages often exceeding 12 billion years, making them among the oldest objects in the galaxy. Many halo stars did not form in the Milky Way at all. They are immigrants, brought here through the merger and disruption of smaller dwarf galaxies. The Gaia Sausage Enceladus merger, for example, contributed a large fraction of the stellar halo's mass. Other mergers, smaller and more recent, have added streams and clumps that are still discernible as distinct structures against the background halo. Globular clusters, those dense spherical collections of hundreds of thousands of stars, are part of the stellar halo. The Milky Way contains more than 150 known globular clusters, and likely more that remain hidden behind dust, or are simply too distant and faint to have been detected yet. These clusters orbit on highly elliptical paths, plunging through the galactic disk and swinging back out to distances of 100,000 light-years or more. They are ancient, with ages similar to the halo stars, and serve as fossil records of the galaxy's early history. Finally, there is the dark matter halo, the invisible component that outweighs everything else combined. This halo extends far beyond any visible structure, reaching at least 300,000 parsecs and possibly to 600,000 parsecs or more. It is roughly spherical but with complex substructure, clumps and streams left over from the galaxy's assembly. The dark matter halo is what holds the entire system together, providing the gravitational glue that binds stars, gas, and smaller satellite galaxies into a coherent whole. Each component has its own characteristic size, mass, age, and chemical composition. Together, they form an integrated system whose total size depends on which component you are measuring. The nucleus spans 400 light-years. The bulge extends 10,000 light-years. The thin disk reaches 50,000 to 100,000 light-years depending on the definition. The thick disk is slightly more extended. The stellar halo stretches to 300,000 light-years, and the dark matter halo may extend to nearly 2 million light-years. Understanding the Milky Way's true size requires appreciating this hierarchical structure. The galaxy is not a simple disk of stars. It is a complex, multi-component system built up over billions of years through processes that are still not fully understood. Each component tells part of the story of how the galaxy formed and evolved, and each contributes to defining what we mean when we ask, how big is the Milky Way? Size is not just a number. It is a fundamental property that reveals how a galaxy formed, how it has evolved, and what its future holds. When we measure the Milky Way's size and compare it to other galaxies, we are not just satisfying curiosity. We are testing our understanding of how galaxies come into existence and what physical processes govern their growth. The revised measurements showing that the Milky Way has a larger half-light radius than previously thought, 18,750 light-years instead of 11,000, have important implications. This larger size places the Milky Way squarely among typical disk galaxies of its mass. It is not an unusually compact outlier. It follows the same size-mass relationship that other spiral galaxies follow. This suggests the physical processes that determine the Milky Way structure are universal, not special to our galaxy. Galaxies grow primarily through two mechanisms: star formation within the galaxy and mergers with other galaxies. The balance between these processes affects a galaxy's final size. Galaxies that experience many mergers tend to be larger because mergers add both mass and angular momentum, spreading the stars over a larger volume. Galaxies that grow primarily through in situ star formation tend to be more compact because stars form in gas that has settled into a rotating disk. The Milky Way's size suggests it has experienced a moderate merger history, neither completely dominated by mergers nor entirely isolated. We know the galaxy has absorbed many dwarf galaxies over its lifetime, the Gaia Sausage-Enceladus merger being the most significant example. But we also know that much of the disk formed through in situ star formation, gas collapsing into the disk and forming stars locally, rather than being brought in through mergers. The inside-out growth pattern revealed by chemical abundance studies supports this picture. The inner regions of the disk formed first, building up a dense core. Over time, star formation gradually extended to larger radii, building the disk outward. This inside-out growth is a natural consequence of how gas settles into a rotating disk. The densest regions, closest to the center, collapse first. As they do, angular momentum conservation prevents all the gas from falling in, leaving material at larger radii to collapse later. This growth pattern explains the broken surface brightness profile discovered in the 2024 studies. The flat region between 11,000 and 24,000 light-years likely reflects a period in the galaxy's history when star formation was particularly vigorous across a wide radial range. The sharper decline beyond 24,000 light-years might indicate a transition to a different formation regime or a change in the gas supply that limited star formation at larger radii. The Milky Way's total stellar mass, now estimated at about 26 billion solar masses if we include stellar remnants, also has implications. This is lower than many previous estimates, suggesting the galaxy is less efficient at converting gas into stars than some models predicted. A lower stellar mass for a given dark matter halo mass implies a lower star formation efficiency or a longer timescale for star formation to deplete the gas reservoir. Comparing the Milky Way to its largest neighbour, the Andromeda galaxy, provides additional context. Andromeda is significantly more massive, with a stellar mass perhaps twice that of the Milky Way, and a total mass including dark matter that may be comparable or slightly larger. Andromeda is also larger in terms of its visible disk, though the two galaxies have similar dark matter halo sizes. This difference likely reflects Andromeda's more violent merger history. Andromeda has experienced more major mergers than the Milky Way, and these mergers have inflated its size and stellar mass. The two galaxies are currently on a collision course. In about 4 to 5 billion years, they will merge, their gravitational interaction shredding both spirals and eventually forming a giant elliptical galaxy. This future merger will dramatically change the size and structure of the combined system, mixing stars from both galaxies and potentially triggering a burst of star formation as gas clouds collide. The size of the dark matter halo has implications for our understanding of dark matter itself. The halo's extent and density profile constrain the properties of dark matter particles. If dark matter consists of weakly interacting massive particles, their velocity distribution and interaction cross-section affect how the halo forms and evolves. Observations of the halo's structure can therefore test different dark matter models, narrowing the range of viable candidates. The tilted triaxial shape of the dark matter halo, revealed by studies of the stellar halo and globular cluster kinematics, suggests a complex assembly history. If the halo were spherical, it would indicate a simple, smooth accretion process. The observed shape implies mergers approach from different angles, depositing dark matter and stars with different angular momenta and creating a halo that has not yet fully relaxed into a symmetric configuration. This has practical implications for dark matter detection experiments on Earth. These experiments search for dark matter particles by looking for rare interactions with normal matter in highly sensitive detectors. The expected signal depends on the local dark matter density and velocity distribution. If the dark matter halo is tilted and has complex structure, the local properties might differ from simple models, affecting detection rates and the interpretation of results. The Milky Way's size also affects our understanding of the galaxy's satellite system. The Milky Way has dozens of known satellite galaxies, ranging from the Large Magellanic Cloud with billions of stars to ultra-faint dwarfs containing only a few thousand. These satellites orbit within the dark matter halo, and their distribution and velocities depend on the halo's mass and size. By studying the satellite system, astronomers can infer properties of the halo that are difficult to measure directly. Recent discoveries have expanded the known satellite population significantly. Gaia data has revealed numerous ultra-faint dwarfs that were too dim to detect in previous surveys. These tiny galaxies, some containing fewer than 1,000 stars, are dominated by dark matter and provide unique laboratories for testing dark matter physics and galaxy formation theories. The fact that they exist and orbit the Milky Way tells us about the halo's ability to retain small substructures over billions of years. Finally, understanding the Milky Way's size and structure is crucial for interpreting observations of distant galaxies. Astronomers use the Milky Way as a template, a detailed example that can be studied in ways impossible for distant galaxies. If we understand how the Milky Way's components relate to each other, how its size connects to its mass and formation history, we can apply those lessons to galaxies billions of light years away, where we cannot resolve individual stars or measure detailed kinematics. The Milky Way is not special in the sense of being unique, but it is special in the sense of being accessible. We can study it in exquisite detail, measuring properties and testing theories in ways that no other galaxy allows. Every measurement of the Milky Way's size, every refinement of our understanding of its structure, contributes to the larger project of understanding how galaxies form and evolve throughout the universe. The lessons learned here echo across cosmic scales, informing our understanding of the entire cosmos. We set out to answer a deceptively simple question: how big is the Milky Way? The answer, as we have discovered, depends on what you mean by big and which component of the galaxy you are measuring. But in every meaningful sense, the Milky Way is vast beyond human comprehension. The visible disk of stars and gas stretches approximately 100,000 light-years from edge to edge, a distance so immense that light, the fastest thing in the universe, takes 100,000 years to cross it. This disk contains between 100 billion and 400 billion stars, each a potential sun, many surrounded by their own families of planets. The sheer scale of this number staggers the imagination. If you counted one star every second, it would take thousands of years to count them all. But the visible disk represents only a fraction of the galaxy's full extent. The stellar halo, that diffuse sphere of ancient stars surrounding the disk, reaches out to 300,000 light-years or more, and the dark matter halo, the invisible scaffolding on which the entire visible galaxy hangs, may extend to 2 million light-years, making the Milky Way 20 times larger than the visible spiral suggests. The 2024 measurements have revised our understanding significantly. The half-light radius is larger than we thought, placing the Milky Way among typical spiral galaxies rather than unusually compact ones. the total stellar mass may be lower than previous estimates, implying dark matter dominates even more than we realized. The disk's structure is more complex than simple models predicted, with different regions having different formation histories. These revisions did not come from a single breakthrough, but from the accumulated weight of data from multiple surveys. Gaia mapped 1 billion stars with unprecedented precision. Apogee measured chemical abundances for hundreds of thousands of objects. Ground-based and space-based telescopes contributed observations across the electromagnetic spectrum. The synthesis of all this data, combined with sophisticated modeling and analysis, has given us the most accurate picture yet of our galactic home. Yet mysteries remain. We still do not know what dark matter is, despite its dominance in the galaxy's mass budget. We are still refining our understanding of how the galaxy formed, assembling clues from the chemical compositions and orbits of individual stars. We are still discovering new satellite galaxies and stellar streams, remnants of the Milky Way's violent past, and we're still working to understand the full three-dimensional structure of the spiral arms and how they influence star formation and galactic evolution. The future of Milky Way research promises even more revelations. Gaia will continue observing, accumulating data that will push distance measurements to greater precision and extend coverage to fainter stars. The mission, originally planned to end in 2019, has been extended multiple times as the spacecraft remains healthy and continues producing transformational data. Each additional year of observations improves parallax measurements, allows detection of fainter objects, and extends the time baseline for proper motion measurements. By 2030, Gaia may have observed some stars dozens of times, providing exquisite measurements of their positions and motions. New ground-based facilities are coming online that will complement Gaia's measurements. The Vera Rubin Observatory in Chile, previously known as the Large Synoptic Survey Telescope, began operations in 2024. This facility features an 8.4-meter primary mirror and the largest digital camera ever built for astronomy, with a resolution of 3.2 billion pixels. The observatory will survey the entire southern sky every few nights, repeatedly imaging billions of stars, galaxies, and other objects. Over a decade-long survey, it will create a vast database tracking how the sky changes, detecting everything from asteroids in our solar system to supernovae in distant galaxies. For Milky Way science, the Rubin Observatory will discover countless new faint stars in the outer halo and in satellite galaxies. It will trace stellar streams with unprecedented sensitivity, revealing the full debris from past mergers. It will measure variable stars throughout the galaxy, extending the cosmic distance ladder to greater distances. And by combining its data with Gaia's, astronomers will create the most complete map of the galaxy's structure ever assembled. The James Webb Space Telescope, launched in 2021 and operating at infrared wavelengths, offers capabilities that complement both Gaia and Rubin. While not designed primarily for galactic astronomy, Webb can observe individual stars in the galactic center and distant regions with unprecedented detail. Its infrared sensitivity allows it to see through even the thickest dust, revealing stars that remain invisible to optical telescopes. Webb can also observe extremely faint, cool stars that emit most of their energy at infrared wavelengths, populations that are difficult to study with other instruments. Future space missions will build on Gaia's legacy. The European Space Agency is planning Gaia's successor, provisionally called Gaia Next, or possibly given a new name, which would extend the astrometric measurements to even fainter stars and improve precision for those already in the Gaia catalogue. The Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission scheduled for launch in the late 2020s, will conduct infrared surveys of portions of the galactic bulge, disk, and halo, measuring distances and velocities for hundreds of millions of additional stars. China's space program has also announced plans for an astrometry mission that would rival Gaia's capabilities, though focused on different regions of the sky and using different observing strategies. If realized, this mission would provide independent confirmation of Gaia's results, while extending measurements to southern sky regions that Gaia observed less completely. Ground-based spectroscopic surveys are becoming more ambitious. The Sloan Digital Sky Survey continues to evolve, with new instruments and observing programs targeting millions of stars for detailed chemical analysis. The foremost facility on ESO's Vista telescope in Chile will conduct multiple spectroscopic surveys simultaneously, including comprehensive studies of Milky Way stellar populations. The WEAVE survey on the William Herschel telescope will map stellar kinematics and chemistry across large areas of the northern sky. Radio astronomy is also advancing. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the world's largest radio telescope, with collecting area exceeding 1 square kilometre. While its primary science goals involve cosmology and studies of distant galaxies, it will also revolutionise observations of hydrogen gas in the Milky Way, mapping the cold interstellar medium with unprecedented resolution and sensitivity. This will reveal the detailed structure of molecular clouds where stars form and trace the distribution of gas in the outer galaxy, where current observations are sparse. Computational capabilities are advancing rapidly, allowing ever more sophisticated simulations of galaxy formation and evolution. The next generation of simulations will include more detailed physics, modelling star formation, stellar feedback, chemical enrichment, magnetic fields, and cosmic ray transport with greater fidelity. These simulations will produce synthetic galaxies that can be compared directly to observations, testing whether our theoretical understanding can reproduce the Milky Way's observed properties in detail. Machine learning and artificial intelligence are transforming how astronomers analyse data. With billions of stars to classify, billions of spectra to analyse, and petabytes of data to search for patterns, human analysis is no longer feasible. Machine learning algorithms can classify stellar spectra, detect anomalies, identify rare objects, and find subtle correlations that human inspection would miss. These techniques are becoming essential tools in modern astronomy, enabling discoveries that would be impossible through traditional methods. One particularly exciting prospect involves detecting individual stars in the dark matter halo at distances approaching the virial radius, nearly 2 million light-years from the galactic centre. These extremely distant halo stars, if they exist and can be detected, would provide crucial constraints on the halo's extent and mass profile. Current surveys can detect only the brightest giants at such distances, but future facilities like the Extremely Large Telescope, with its 39-metre primary mirror, may be able to detect fainter populations, extending our reach to the very edge of the galaxy's gravitational influence. Understanding the connection between the Milky Way and its satellite galaxies will continue to be a major research focus. The Large and Small Magellanic Clouds are massive enough to gravitationally affect the Milky Way itself, potentially helping to create the warp observed in the outer disk, and possibly triggering bursts of star formation as their gas interacts with the Milky Way's disk during close passages. Detailed studies of these interactions will reveal how galaxies exchange mass and angular momentum through tidal forces, processes that are important for understanding galaxy evolution throughout the universe. The upcoming collision with the Andromeda galaxy, expected in about 4 to 5 billion years, represents the Milky Way's future. Simulations of this merger show it will be a spectacular, complex event, reshaping both galaxies and eventually forming a giant elliptical galaxy. While far in the future, understanding what will happen requires knowing the current properties of both galaxies, their masses, their dark matter distributions, their current velocities. Every improvement in our knowledge of the Milky Way's size and mass refines predictions for this ultimate encounter. There is also the possibility of detecting gravitational waves from the Milky Way. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will be sensitive to gravitational waves at lower frequencies than ground-based detectors like LIGO can access. LISA should detect gravitational waves from compact binary systems throughout the galaxy, pairs of white dwarfs, neutron stars, or black holes spiraling together. These detections will provide a completely new way to probe the galaxy's structure, using gravity itself as a messenger rather than electromagnetic radiation. The question of life in the galaxy adds another dimension to understanding its size and structure. If life is common, the galaxy may host billions or even trillions of habitable worlds. If life is rare, we may be among the few inhabited planets in the entire structure. Either answer has profound implications. The search for biosignatures in exoplanet atmospheres, the search for technosignatures from extraterrestrial civilizations, and the ongoing investigation of life's origins on Earth all connect to the broader question of our place in the galaxy. As we continue to refine our measurements of the Milky Way, we're also refining our understanding of ourselves. Every measurement of the galaxy's size is a measurement of our cosmic address, a determination of the scale of our home. We have progressed from thinking we occupied the centre of a small cosmos to recognising ourselves as residents of an outer spiral arm in a galaxy that spans 2 million light-years, including its dark matter halo, one of hundreds of billions of galaxies in the observable universe. This is simultaneously humbling and awe-inspiring. The Milky Way is not special in the sense of being unique, but it is special in the sense of being accessible. We can study it in exquisite detail, measuring properties and testing theories in ways that no other galaxy allows. Every measurement of the Milky Way's size, every refinement of our understanding of its structure contributes to the larger project of understanding how galaxies form and evolve throughout the universe. The lessons learned here echo across cosmic scales, informing our understanding of the entire cosmos. Standing here on Earth, a tiny planet orbiting an unremarkable star in the outskirts of a spiral galaxy, we can look out at the cosmos and understand, at least in part, the immense structure that contains us. We know we live in a disk 100,000 light-years across, embedded in a halo 2 million light-years wide. We know this disk contains hundreds of billions of stars, most with their own planets. We know the galaxy formed billions of years ago through the gradual assembly of smaller structures, and we know it will continue to evolve, eventually merging with Andromeda to create something new. This knowledge is precious. For most of human history, we did not even know we lived in a galaxy. We thought the Milky Way was a phenomenon in Earth's atmosphere, or perhaps a celestial river. Now we know it is a colossal wheel of stars, one of hundreds of billions in the observable universe, and we have measured its dimensions with remarkable precision. The journey from ignorance to understanding has taken centuries of observation, measurement, and theoretical work. Harlow Shapley's revolutionary measurements in 1917 established the basic scale. Decades of subsequent work refined the details. And now, in 2024, we stand at a remarkable moment where our maps of the galaxy have reached unprecedented accuracy and comprehensiveness. But the work is far from done. Each answer raises new questions. Each measurement reveals new complexities. The Milky Way is not a static, simple object. It is dynamic, evolving, complex, full of structures and phenomena we're only beginning to understand. Studying it is a project that will occupy astronomers for generations to come. So the next time you look up at that pale band of light stretching across the night sky, remember what you are seeing. You're looking at your home from the inside, a cosmic city containing hundreds of billions of stars, stretching across 100,000 light-years of space, embedded in an invisible halo of dark matter nearly 2 million light-years wide. You are seeing light that has travelled thousands of years from distant suns, crossing the galaxy to reach your eyes, and you are witnessing one of the grandest structures in the universe, a spiral of stars and gas and dust that has been slowly turning for billions of years and will continue to turn for billions more. We finally know how big the Milky Way is, and the answer is bigger than we imagined, more complex than we expected, and more beautiful than we dared to hope. The visible disk spans 100,000 light-years. The stellar halo reaches 300,000 light-years. The dark matter halo extends to 2 million light-years. But beyond these numbers lies something more profound, the realization that we are part of something vast and ancient, a cosmic structure whose full story we're only beginning to read. If you found this journey through the cosmos enlightening, hit that like button and subscribe to Space Reports for more deep dives into the mysteries of the universe. The Milky Way is vast, but there is still so much more to explore.